Hello, this is going to cover our last chapter for introductory chemistry. This chapter is called Solutions. So this one is pretty half and half mix of concepts and math. So we're going to talk about some of the words that describe solutions and their properties, and then we'll get into the math side. So first we just need to define the word solution, and we've actually done this. It's been quite a few chapters, but all the way back in, I think it was chapter 2, we defined homogeneous and heterogeneous mixtures, and a homogeneous mixture is really a solution. So if we use that definition and that phrase, we can say that a solution is when we have two or more things mixed together that looks like the same thing, and the composition, so that ratio of ingredients, can vary from part to part. Now, a lot of times when we hear the word solution, we might think it has to be a liquid, but that's not the case. So I have a couple examples down here. So the first one over here is whipped cream. Whipped cream is a mixture of a liquid, so a dairy product, some milk or cream, mixed with carbon dioxide. And so this is a liquid and a gas mixed together to give us whipped cream. The middle one is brass. And brass is a solution made from two different solids. So it's copper and zinc mixed together. And those can come in different percentages, and it will change the color and the shine of the brass. And when we have two different metals mixed together, it's called an alloy. So you might have heard that term before, but an alloy is a metal solution. And then the third one is soda. And soda is definitely a mixture of different things. So there's solids in there like sugar, and there's different liquids in there like coloring and water, and there's gas in there, the carbon dioxide, the carbonation. And so solutions can come in all different forms. What we are focusing on are aqueous solutions. So for the majority of the chapter, when we will be focusing on the aqueous side of the solutions. So we do have two words here to define though. The first one is solute, and the solute is what gets dissolved. And so it usually kind of looks like it's disappearing. We can even say that it's taking on the state of the solvent. So for example, down here we have this blue powdered solute, and when we mix it, we get this blue solution. So it almost looks like it has become a liquid. Now that's not technically the case, but for appearance wise, that's what we can say. Now, the other way we can describe it is that the solute is in the smaller amount if we're comparing our solute and the other half, which is the solvent. The solvent is what does the dissolving, and it does not change state, and it's going to be in the larger amount. So in the example down here, this blue powder is our solute, the water is our solvent, and when we add those together, we get our solution. And if water is our solvent, then we can call this an aqueous solution. So aqueous really just means that we have a solution and water's the solvent. It gets a special name though because we use it so often. Will it dissolve? So will something become a solution? Now we've actually answered this question before in a couple different chapters. We have our solubility table from a previous chapter, and in our chapter 10, I believe it was, when we talked about polarity, we talked about like dissolves like, and we've talked about intermolecular forces. So this is kind of just wrapping all of that together. Oh, that's my cat. So there's three different attractions shown on here, and the one that we're focusing on is this one right in the middle, the solvent-solute attraction. That attraction has to be strong enough to overpower the solute-solute attraction, and the solvent-solvent attraction. So the example that's on here is NaCl, so sodium chloride, and that is a small enough attraction that when we put that into water, it will be able to dissolve it. The water molecules will be attracted to the sodium cations and the chloride anions. So we know that ions are attracted to polar solvents. That's our ion dipole attraction that we learned about. And we also know that polar molecules are attracted to other polar molecules. So this is our dipole-dipole attraction. And nonpolar are attracted to nonpolar. And this is our London or our dispersion forces. Now, it's difficult to mix something that is polar with something that is nonpolar, because in order to do that, we would have to separate the polar molecules from each other. We'd have to separate the nonpolar molecules from each other, and then put the polar and the nonpolar together. But if we go back to this picture, if that's what we're trying to do, mix a polar with a nonpolar, the polar is very attracted to itself, and the nonpolar is very attracted to itself, and the attraction to each other isn't enough to pull those other molecules away from each other. So that's why we use that phrase like dissolves like, because they have to have enough in common in order for that attraction to be strong enough. The words soluble and insoluble, we've also seen those. Soluble means that it will dissolve, and insoluble means that it will not dissolve. So here's just one more picture of why the sodium chloride dissolves. So we have our sodium chloride in solid form. We put it into our water, so now we have our solvent and our solute, and all together they make up a solution. And what's happening is those water molecules are grabbing onto the sodiums and the chlorines, and again, notice that the partially positive hydrogens are pointing towards that negative chlorine, and the partially negative oxygens are pointing towards that positive sodium. So we have that strong ion dipole attraction. And then the other word that we use for this is that we can say that they are solvated ions. This process that's happening right here is called solvation. Now, when something does dissolve, we have a couple different words to describe this, and we're actually going to describe it a few different times. We're going to describe it based off of qualitative words and quantitative words. So qualitative is more just of a description, and then quantitative is when we bring in our numbers. So first, the word solubility. There is a maximum amount of solute that can be dissolved. And so the solubility is that number. It's the maximum amount of solute that can be dissolved in a given amount of solvent. And so based off of that, we have these three terms. And so these each represent a different level of solute in a solution. So I'm actually going to start with the middle one right here, unsaturated. An unsaturated solution means that we are below the solubility level. And that means that if we add more solute, it will still dissolve. So I always like to think about this with like an iced coffee reference. So if you put sugar in your iced coffee, it will dissolve, but it's going to reach a point, it's going to reach its solubility level where it won't dissolve any more sugar. And so when you are at that point, you have a saturated solution. So this is the maximum amount of solute you can add, and if you try to add more, if we try to add more sugar to our iced coffee, it just won't dissolve. It will sit on the bottom of the cup. And then the last one down here, a supersaturated solution. If we heat a solution up, it will dissolve more solute. So if we go back to our iced coffee, if you think about iced coffee versus hot coffee, or iced tea versus hot tea, the hot tea and hot coffee dissolve more sugar than their iced counterparts. Having more energy, having more temperature and heat helps to separate those solute particles, and it will dissolve more. So what we can do is we can heat up a solution, add a bunch more solute to it, and then cool it down very slowly. And if this happens, we create a supersaturated solution. So the definition is that it's a solution that has more solute dissolved in it than it should. And this is unstable. What that means is that if we add more solute to it, that won't dissolve, plus all of that solute that's above the solubility level will also turn back into a solid. So I have a little video here. Oh, let's not do that. Oh, it won't let me. Okay. Wouldn't let me not cancel that. All right, so here's the video.
Okay, just really quick, I'm going to add one tiny seed crystal. I'm not sure if you can see on the tip of that scoopula there. Right at the tip, we're going to add that to my supersaturated solution of sodium acetate. And we will see it go from a supersaturated state to a saturated state in just a few seconds. Isn't that cool? So we see that the sodium and acetate ions recognize the crystalline structure of that seed crystal I just added, and they add to it, and we form one big crystal. And when I tilt this to the side, you can see it looks like a big chunk of ice, doesn't it? So now we're back. There's a little bit of water in there. You might be able to see it, but we're back to our saturated state right now. So we've gone from supersaturated to saturated in just a couple of seconds.
So that solution was, let's see, there we go. That solution, when he started, was supersaturated. So that means he had to create it by heating it up and cooling it down. And then when he added that one tiny, I don't even know if you could see it on the spatula, but there was one tiny little crystal. It looked like one little piece of salt. He added it into that solution, and all those crystals started growing. That was the formation of all of that solid that was above that solubility level. So we've also defined electrolytes, but this is part of our solution, so we're adding this in here as well. We know that an electrolyte is any solution that will conduct electricity, so really that just means it has ions in it. Oops. And we can divide that into our three categories here. So our strong electrolytes are solutes that completely break apart into their ions. So when we had our solubility table, these are ionic compounds that we labeled as soluble. So soluble ionic compounds. So the example that we usually use is NaCl. Non-electrolytes are things that don't break apart into ions. And so these are our molecular compounds. And so the example down here is sugar. Now when we put sugar in our coffee and our tea, we don't see it anymore. It does dissolve, it is soluble, but it's not breaking apart into ions. It doesn't contain any ions. When we drop that sugar in there, each sugar crystal contains lots and lots of molecules of sugar, so it's just separating into individual molecules that are too small to see. And then the last category are weak electrolytes. And these are molecules where a small amount of the molecules break apart into ions. And so this is where things like weak acids fit in. So the example we like to use a lot is hydrofluoric acid. So some of them break into hydrogen and fluoride ions, and some of them stay together as HF molecules. So I did talk about how solubility is related to temperature when we were looking at our supersaturated solution. So here's just a little bit more on that. A higher temperature means that the solubility of a solid in a liquid is going to increase. So this chart, we have temperature on the x-axis, we have solubility on the y-axis, and notice that all of our lines here are pointing up. Now some are in a much steeper slope than others, but what that means is that if we have a solution at a temperature of 10 degrees, so we're just going to pick out 10 degrees, and let's look at the green line here, potassium nitrate. What that tells us is that at 10 degrees, 20 grams of potassium nitrate could be dissolved in 100 grams of water. But if we take that temperature and now raise it to 40 degrees, we can now dissolve approximately 64 grams of potassium nitrate in 100 grams of water. So this type of data can tell us what that solubility number is based off of the temperature. Now, I want to point out again, I did say it, but this is the trend for solids in liquids. I point that out because here's our other trend. If we are dissolving gases in liquids, so think about our carbonation, our CO2 dissolved in our soda, at higher temperatures, we will have lower solubility. Or, to flip that the way it's typed, at lower temperatures, we will have higher solubility. And this is something we know, because if you have soda that you open up and it was cold in the fridge, it fizzes a little bit when you open it up. But if you have a bottle of room temperature soda and you open it up, it's going to get very, very fizzy. So this is the one that was warm when it was opened up, and this is the one that was cold. So because that gas can't stay in the liquid as well, it's fizzing out and it's leaving the solution. There's also a relationship between solubility and pressure when we're talking about gases. So again, this is just for gases in liquids. When we have a higher pressure, we have a higher solubility. So if we have a high pressure of gas, it's pushing all of those gas molecules into the liquid. And again, we know this. So we have our cans of soda here. Here's our high pressure. So that means there's just more gas molecules in there to create that high pressure. It's pushing the gas molecules into that soda, into that liquid. When we have the can of soda and it's still closed, it's under pressure and the soda is fully carbonated. But as soon as you open that and you hear the psh, you get that release of carbon dioxide. Now it's not under pressure anymore. And so as soon as you've opened that, your soda is going to start to go flat because the carbon dioxide has an escape route. And as you're drinking it and it warms up, the solubility is going down for that reason as well. You're giving those gas molecules more energy through the temperature change so that they can escape from the solution into the gas phase. So 2 more words, and then we're actually switching over to the math side. But the 2 words we use to describe a solution's concentration are dilute and concentrated. Now remember, when we have a solution, it means that the components, the solute and the solvent, can be in varying concentrations. So again, if you think about this like a cup of coffee, if everyone in here makes some coffee and we've all put sugar in our coffee, everyone's made coffee with sugar, but the amount of sugar, that sugar to coffee ratio, is probably going to be very different from person to person. And so we use these terms to describe it. Concentrated is when we have a large amount of solute. So if you put lots of sugar in your coffee, you can say it's concentrated with sugar. And if you put a small amount, it's dilute. So it's a dilute amount of sugar. So these 2 words are describing the amount of solute. But high and low, they're real subjective. I personally like my coffee black. So any amount of sugar would be concentrated to me because it's much more than I would want. These words are really good for comparison purposes. So if we're looking at these blue solutions down here, we can definitely say that this one is more concentrated than this one, and this one's more concentrated than that one. But outside of comparison purposes, these words don't hold a lot of meaning. We have to have some standard to compare them to, or comparing them to one another. So that means we need some quantitative definitions. And so again, our solutions have that variable composition. So to give them a true description, we need to say how much of our solute and solvent are in the solution. And so we're going to talk about different ways to calculate concentration. And usually this is going to be the amount of solute for a given amount of solution. Sometimes it's the amount of solute for a given amount of solvent, but that one's not as common. So here's where we're starting. We're going to start with mass percent. And we've actually calculated mass percent before for chemical compounds. So whenever we're doing mass, or whenever we're doing a percent, the general formula is always the same. Part divided by whole. So here's our idea here. And we have an IV bag there with 0.9% sodium chloride solution. So if a solution is 0.9%, that means that there are 0.9 grams of solute for every 100 grams of solution. And so here's our equation down here. The mass percent is equal to the mass of the solute divided by the mass of the solution times 100. And that mass of the solution is the mass of the solute plus the mass of the solvent. So you might not need that second equation. It just kind of depends on what information is given. We're going to do a practice one after this slide, but I want to also point out that this number can be used as a conversion factor. And again, we did something similar to this when we did our mass percent of formulas, of chemical formulas. So if we had a solution that was 12% sugar, that means that our conversion factor here could be 12 grams of sugar for every 100 grams of solution. So here's kind of our general form. That mass percent can be the number of grams of solution for every 100 grams, or I think I said that backwards, excuse me, the number of grams of solute for every 100 grams of solution. So here's how we're going to practice this. What is the mass percent of a bleach solution that is made from 25 grams of NaOCl, which is sodium hypochlorite, and 550 grams of water? I know that this is my solute, and this is my solvent. And the reason I know that is because of quantities. So the 25 grams is definitely the smaller amount. So I know, excuse me, I know that that will be my solute. So if we want to know mass percent, we need to know grams of solute divided by grams of solution. I pointed this out in a previous chapter, but be careful with your abbreviations. I just wanted to abbreviate solute as SOL, but that's the same first letters as solute, solvent, solution. So just something to keep in mind as you're doing your own notes. So we know the mass of the solute, 25 grams, and we don't know the mass of the solution, but we have enough information to find it. 25 grams plus 550 grams. And then we're going to multiply this whole thing by 100 because it is a percentage. So I'm going to put that in my calculator. I have 25 in my numerator divided by the 25 plus the 550 and then times 100, and I get 4.3478, and we're going to check units and sig figs. Now, units, mass percents don't have units because we ended up with grams over grams, so they canceled out. So really, our units are just the percent sign. And then sig figs, what we started with, each thing had 2, so I'm going to underline that guy. So we end up with 4.3%. The second question says, how many grams of NaOCl are in a cup of bleach? And we're told that that cup of bleach weighs 230 grams. So we know we can use our new number as our conversion factor because 4.3 grams of NaOCl are in 100 grams of the solution, which is the bleach. So we have our nice conversion factor. We have our given, the 230, so 230 grams of bleach. I'm going to use my conversion factor here, grams of bleach on the bottom, grams of NaOCl, and then I can fill in my numbers. So the 4.3 on the top, 100 on the bottom, and again, I'm going to put that right in my calculator. 230 times 4.3 divided by 100, and I get 10. I get exactly 10, actually. Well, let's use the 4.3. 9.89. There we go. Okay, so sig figs and units. I started with 2 significant figures, so I'm going to cut it right there. So I get 9.9 grams of bleach cancel, and we are left with grams of NaOCl. There we go. There's a lot of ways to calculate concentrations. There's a lot of different uses for it. So that mass percent that we just saw isn't actually used a whole lot in chemistry. It's used a lot more in biology, especially in the medical field. That's why we used, excuse me, that's why we used an IV bag for our example. The one that we use a lot more in chemistry is called molarity. And molarity is the moles of solute for every 1 liter of solution. So we use this more in chemistry because we're dealing with moles. So we know that that's our go-to counting. And because we're normally talking about aqueous solutions, that means that they are liquids. So we're measuring them in volumes, so a liter. So the example on here, it says if a sugar solution is 2.0 molar. Now notice how this is written, 2.0 with a capital M, and it does have to be capital. A lowercase m means something else. We'll talk about that in a few slides. The other way to write this, though, is 2.0 moles per liter, and they both mean the same thing. I actually prefer the moles per liter because you can see both units, and we are going to be using that as a conversion factor. So here's some other ways to say that same piece of information. 1 liter of solution contains 2 moles of sugar. 2 liters of solution will contain 4 moles of sugar. And half a liter of solution will contain 1 mole of sugar. So essentially we're kind of using it as a conversion factor right there, just based off of that ratio. And here's our equation down here. Molarity is equal to moles of solute divided by liters of solution. So we're going to talk about how to make this solution, like what it means first, and then we are going to do some math with it. So here is our solution. We're making a 1 molar solution of NaCl. So first we weigh out 1 mole, which is 58.45 grams of NaCl, and it's put into a 1 liter flask. Then the water is added, and not all the way. Notice it's only up to here-ish. It's added, it's swirled around. Here's my little symbol for swirling it to get all of that to dissolve. Then more water is added. So notice this little line that's up at the top. So that line is right here as well. The rest of the water is added so that it's up to that line. And it kind of seems silly that we're talking about how to make this, but there's a reason for it. It has to be done in this order. Solute has to be added first. Because if we did this in the opposite order, we filled the water up and then added the solute, the water would go, or the solution would go above that line. And we need 1 liter of solution, not 1 liter of solvent. So there's a little bit of a difference there. Okay, so here's our practice for molarity. What is the molarity of a solution made from 23.4 grams of sodium sulfate with a total volume of 125 milliliters? So we need moles of sodium sulfate on the top and liters of solution on the bottom. So I don't have either of those numbers, but I have enough information to figure out both. So I know I have grams, I need to convert that into moles, and I have milliliters, I need to convert that into liters. So a lot of times with these concentration problems, I write down what I'm trying to solve for, and then solve for each of those pieces separately, and then put them together in my formula I care about. So I'm going to start with my 23.4 grams of my sodium sulfate, and I know to go from grams to moles, I'm going to use my molar mass, and my molar mass is 142.04 grams for 1 mole. Started really high because I knew I would need some space. I ran into my other part here. All right, so I'm gonna put that in my calculator. 23.4 divided by 142.04, and I get, I'm gonna do that, there we go, 0.16474 moles. I'm not going to round it, but I will underline. So we had 3 significant figures to start with, so I'm going to underline that 4. And then I have 125 milliliters. Now you might be able to convert milliliters into liters in your head, and that's completely okay. 1 milliliter is 10 to the negative third liters, so we get 0.125 liters. And then we're going to take these two numbers, and we're going to put them into our formula. I'm going to switch colors so we can see it a little better. Fill in my units, moles per liter. So then we do our number of moles. Oh, I put liters twice. Let's put a 5 in there. There we go. Divided by 0.125. And we get 1.317938. So sig figs in units. It looks like we have 3 sig figs all the way around, so we're going to round this to 1.32, and I'm going to write it as moles per liter. The other way we could have written this answer is 1.32 with just a capital M. All right, the second question says, what volume of the above solution would contain 5.5 grams of sodium sulfate? Well, we know that there are 1.32 moles of sodium sulfate in 1 liter of solution. And we're starting with grams, so if we go from grams to moles, we can use our molarity as a conversion factor to get to volume. So 5.5 is my starting point. And we already know the molar mass because we used it in the above problem, 142.04. And then I can use my molarity. So moles go on the bottom because I want them to cancel out. Liters of solution on the top. So when I look at this, I have 1 liter of solution for every 1.32 moles. And then it asks for volume, so I'm going to leave it in liters. We put this in our calculator, 5.5 divided by 142.04 times our molarity. And I get 0.02938. Sig figs in units. Looks like our starting number only had 2 significant figures, so I'm going to underline that 9, because remember those leading zeros do not count. Units, grams of sodium sulfate are canceling, moles of sodium sulfate are canceling, we're left with liters of solution. So 0.029 liters of solution. Now that's not the best way to write that. We could convert it over to milliliters. So both of those would be right answers, just kind of depends on what's asked. So this one didn't specify units, so both of those would work. If we have an ionic compound, when it dissolves in solution, the ions are separating. And so we can figure out the ion concentration from the molarity and the chemical formula. So here's our example. If we have a 0.075 molar solution of iron 3 carbonate, so Fe2CO3, we can figure out the concentrations of each of our ions. So notice that Fe3 plus is written in brackets. When we write something in brackets, that actually means molarity. So the molarity of the iron 3 plus cation is going to be the molarity of the overall molecule times its subscript. So the molarity of the iron is 0.15 molar. The molarity of the carbonate is the same formula, so 0.075, and times a 3, because there's 3 carbonates. And so we would get 0.225 molar. Now we're not calculating the molarity of the oxygen or the carbon separately, because carbonate isn't ionic within that polyatomic. Remember, those are covalent bonds. So we can calculate the concentration of a cation or an anion. Oh, there we go. A lot of times when chemicals are stored, they're stored in very concentrated amounts, and then when they are used, they are diluted back down. And so in this process, we take a small amount of that concentrated solution and add a bunch of solvent to it, so water most of the time is what we're talking about. And when we do this, the amount of solute is going to stay the same. But because the solvent amount increases, that means the concentration is going to decrease. So we can use this equation here, it's called the dilution formula, to figure out new molarities. So this is the molarity of the original solution. So this is molarity of original. And this is the volume of that original solution that is going to be used. This is the new volume. So it's the original volume plus however much solvent was added. And then this is our new molarity after that dilution has taken place. So let's look at how we would use this in a formula. So here's our situation right here. We're going to make 5 liters of a 1.5 molar KCl solution from a 12 molar stock solution. So over here's the math to go along with that. So our original solution has a molarity of 12 molar, and the solution we're trying to make has a molarity of 1.5 molar and a volume of 5 liters. So in our equation, this is the piece that's missing. How much of that original solution needs to be used? So we take our original equation, we do a little bit of rearranging, and then we can plug in our numbers. So we have the new molarity times the new volume divided by the original molarity, and we get 0.625 liters. So here's how we utilize that information. We take 0.625 liters of that original solution. It's in this container is a 5-liter flask. And so then we add water to this container until it has a total volume of 5 liters. And when we add that 5 liters, we get our new concentration of 1.5 molar. So this could also help us figure out how much water we needed to add. If we do the 5 liters minus the 0.65, that tells us we would need to add 4.375 liters of water. All right, we're going to do some math. How many milliliters of 3 molar H2SO4 are required to make 450 milliliters of 0.1 molar? So let's write down what we know. How many milliliters? That's what we don't know. That's what's being asked. Of 3 molar H2SO4 are required to make 450 milliliters of 0.1 molar H2SO4. So I have my more concentrated solution, the 3 molar, and I want to know how much I need. So M1V1 equals M2V2. So I'm solving for V1, so I'm going to divide both sides by M1. It cancels out over here. We're left with V1 is equal to M2V2 over M1. So we're just going to plug in our numbers. M2, I had that labeled wrong. There we go. M2 is 0.01 molar times volume 2 divided by molarity 1. So we're going to put that into the calculator. 0.1 times 450 divided by 3. So I get 15. So we're going to check sig figs in units. And my molarity is canceling out. I'm left with milliliters. Our volume can be in actually any unit we want as long as we're consistent. So the volume 1 and volume 2 need to be the same unit. We started with 2 significant figures, and so we're going to end with 2. So we get 15 milliliters. So to kind of talk about what that number means, we would use 15 milliliters of our 3 molar solution, put it into a flask. Because we want to make 450 milliliters, we're going to add 435 milliliters of water to that 15 milliliters. That's going to water it down or dilute it down. So now we have a concentration of 0.1 molar. Stoichiometry. So we are not quite done with our crazy stoichiometry map. We know that our balanced chemical equation gives us ratios. We know that molarity is a ratio between moles and liters. So now we can measure how many moles are needed or created based off of molarity and volume. So here is our map. I changed the colors a little bit just to kind of see the division a little better. But what's been added is this part right here. So if we know the molarity, that will connect us between moles and volume. One more thing I want to point out on here. So we have gas, we have volume, and we have grams. So if we're starting with a solid, we're going to most likely start with grams. If we're starting with a solution, we'll start with volume. And if we're starting with a gas, we'll start with our ideal gas law. But this allows us to start or make any of our states that we have. Now the one that's not on here is just a pure liquid, but we know that with a liquid we could use density to go from mass to volume. So that could be one more little spoke on this crazy wheel. I'm going to save this as just a PDF and put it up on Canvas for you so that you have that full reaction map to reference if you'd like. So we're going to do a practice one. How many grams of water are produced in the following reaction if, that should be an if 25 milliliters of 0.1 molar HNO3 reacts. So going back, we know a volume and a concentration, and we're trying to find grams. So we are right here, we have a volume and a concentration that will get us to moles. Then we're going to use our mole ratio to get into moles of water, and then we're going to use our molar mass to get into grams. So we're making this little turn right here to do this problem. First things first, it needs to be balanced. So I'm going to think of water as HOH in order to balance this. I have calcium, hydroxide, hydrogen, and nitrate. 1, 2, 1, 1, 1, 1, 1, 2. So not too terrible. I'll start with the nitrates. I'm going to put a 2 right there. So now I have 2 hydrogens and 2 nitrates. And then to balance off those hydrogens, I can put a 2 right here. And so now I have 2 hydrogens and 2 hydroxides. So it looks like everybody is balanced and happy. So I'm going to erase my work for that just so I have enough space to do the math for this problem. There we go. So in order to find the math for this, we have to have that ratio. So we're given two numbers, volume and molarity. Molarity is a conversion factor. So I know that my starting point is that 25 milliliters. I'm going to put the chemicals up above just to save myself some space. Now that 0.1 molar, I know that that means 0.01 moles for every 1 liter. I'm not in liters though, I'm in milliliters. So I'm going to show you a little trick just to kind of combine two steps into one. There are 1,000 milliliters in a liter. So instead of saying 0.1 moles per liter, what we can say is there's 0.01 moles for every 1,000 milliliters. So it's saying the exact same thing. It's actually just skipping a step, or really combining two steps. Now what we want to find is how many grams of water are we going to make. So I'm in moles of nitric acid. I'm going to convert that over, moles of nitric acid into moles of water. So I look at my chemical equation, my balanced chemical equation, it's a 2-to-2 ratio. And then my last step, we're going to go from moles of water to grams of water. And I'm going to put all this in my calculator. I have 25 times 0.1 times 2 times 18. So that's just the top half. And then 1,000 times 2 times 1 So nice numbers. So 90 divided by 2,000, make it 0.045. We're going to check significant figures and units. Milliliters are canceling. Moles of nitric acid are canceling. Moles of water are canceling. We're left with grams of water. Both of these are given. So we have 3 significant figures versus 2. So we're going to keep 2, which is right where we're at. So I'm just going to add grams of H2O. And there we go. There's our final answer. So we have kind of one general topic left. There's a couple sections in the book that cover this, but one topic left. And it kind of starts with just saying, why do we do that? And it's talking about why do we put salt on icy roadways and antifreeze in our cars. And the reason why is because when we add solute to a solvent, it changes the freezing point and the boiling point. It makes them more extreme. These are called colligative properties. A colligative property is when a solution's property depends on how much solute is in it. And the properties of a solution are different than a solvent. So the 3 we're going to look at are freezing point, boiling point, and a little bit about osmotic pressure. So we're going to do math with the first 2. The freezing point of a solution is always lower than the freezing point of a pure solvent. This is called the freezing point depression, so it's getting lower. That's why we are depressing it. Here's our equation we're going to use for this. So the delta T is equal to M times K. The delta T is telling us how much lower our freezing point is going to be. So if we take the freezing point of the pure solvent minus that freezing point of the solution, that will give us our delta T. M, we're going to look at on the next slide. This is a new concentration. It is called molality. And then Kf is the freezing point constant. So this is usually provided, or it's something we would look up in a table in our book, but it's unique to each solvent, and it is a constant, so meaning it doesn't change. Oh, and a lot of times this can be used to figure out molar masses. So let's talk about that molality value. Molality is moles of solute per kilogram of solvent. So it's it's a little bit similar to molarity. They both have the same numerator. They both have moles of solute on the top, but their denominators are very different. And the reason why we use molality in this case is because it does not change with temperature. We know that when we freeze water, it expands. So if we're calculating moles per liter, the volume is increasing when we freeze something, so the molarity is not consistent. But if we're doing it based off of masses, it's not going to change. And so molality stays consistent no matter what the temperature is. So here's our equation. Molality equals moles of solute over kilograms of solvent. It's abbreviated with a lowercase m. So this is why it's very important to write molarity with a capital M and molality with a lowercase m. So here's our practice question. What is the freezing point of a solution made from 4.35 grams of SO2 and 25 milliliters of benzene? And then we have some information there. The freezing point of benzene is 5.53 degrees Celsius. The Kf for benzene is 5.12. Look at the units here. Remember, constants have weird units. Degrees Celsius times kilograms over moles. And then the density of benzene is 0.879 grams per milliliter. So eventually we want to say delta T is equal to K times M. We have K. We need to find M. So we know that M is moles of SO2 divided by kilograms of benzene. Well, we have the grams of SO2, so we know we can take that and turn it into moles using molar mass. And we have the milliliters of benzene and the density. So with those two pieces of information, we can get to grams, and then from grams to kilograms. So we have all the pieces. It's just going to take a little bit of work to get there. So 4.35 grams of SO2. And we're going to use its molar mass, grams on the bottom, moles on the top to get to our moles. And the molar mass of SO2 is 64.066 for 1 mole. Grab my calculator here. 4.35 divided by 64.066. And we get 0.067898 moles. I'm going to underline my sig fig here, but not round. So we're going to cut it off at that third significant digit, that 8. And then I have 25 milliliters of benzene. And I want to convert that into kilograms. So I'm going to use the density. My density is in grams per milliliter, and the density is 0.879 grams per 1 milliliter, but I want that to be in kilograms. So I'm going to have 1 kilogram on the top and 10 to the third grams on the bottom. So 25 times 0.879 divided by 10 to the third, and we get 0.021975 kilograms. Same thing, I'm going to underline my significant digits. It looks like I get 3 again. So I'm going to take those two numbers and combine them. I'm going to do it down here, 0.06789 moles divided by 0.021975 kilograms. And we get 3.0898. And we can write this as a little m, or we could write it as moles per kilogram. 3 significant figures. So my molality, 3.09 moles per kilogram. Now that's not actually what the question's asking. We're asked what is the freezing point. So going back to my original equation over here, I'm just going to rewrite it up here. Delta T is equal to K, which was given, 5.12 degrees Celsius times Kelvin over moles times my molality, which we just figured out, so 5.12 times 3.09, and we get 15.8, because I'm going to keep my 3 significant figures. Notice the units, moles and kilograms are canceling out. We're left with degree C. That's still not the answer, though. We want to know what the new freezing point is. So the original freezing point is 5.53. Freezing point depression means that we're always going to go down. So I'm going to subtract the 15.8. And I get negative 10.3 degrees Celsius. So adding in that SO2 into the benzene will reduce my freezing point by 15.8 degrees. And so my new freezing point is negative 10.3 degrees Celsius. Boiling points are going to do the same thing. They're going to get more extreme. So the boiling point of a solution is always higher than the boiling point of a pure solvent. Notice the equation down here. It looks very similar. Delta T is equal to the molality times K. The only difference in this equation compared to the freezing point one is that it has little b's here for boiling. The other one had little f's for freezing. So we're going to use our information we already calculated on our last practice problem. It says, what is the boiling point of the SO2 benzene solution? So we know that the delta T is equal to K times M. So I'm going to go back. What was our molality? Our molality was right here, 3.09. So I'm just going to plug that into my equation. Delta T is equal to K, which is given right here, 2.53 degrees Celsius times Kelvin, not Kelvin, excuse me, kilograms, over moles, times the molality, which is 3.09 moles per kilogram. So I put that into my calculator, 2.53 times 3.09, and the delta T is 7.8177. Moles are canceling, kilograms are canceling. We're going to keep 3 sig figs there. This isn't our answer though. Our boiling point is going to be the original boiling point. Oh, sorry, there's a little typo there. That should be boiling point. 80.1 degrees Celsius plus our change in temperature. So we take our original boiling point, we add this change in temperature, and we get our new boiling point, 87.9177. We're going to stop it at that first decimal place because we're adding. So remember, those are our addition rules. So we get 87.9 degrees Celsius. All right, last topic in this chapter is osmosis. And osmosis is when a solvent flows from a less concentrated area to a more concentrated area. So this is called a U-tube, actually, which always kind of makes me laugh. But we have just water on the right-hand side, and we have water with a solute on the left-hand side. And the water can pass through this middle divider here. It's a semi-permeable membrane. So that means the water, the solvent can get through, but the solute can't. And so the water is going to go towards the left side, the more concentrated side, to essentially even out the concentrations. And so what we end up with is a volume that's higher on the left than it is on the right. The last term we need to know is osmotic pressure. The amount of pressure we would need to push down on this side to prevent this from happening is called the osmotic pressure. Okay, that is it for chapter 13, and that is it for our lectures for our introductory chemistry class. Thank you.